Alright guys, welcome back to Underground Science, and in this video we're going to be continuing where we left off from the part 2 video of insulin synthesis. Alright, so if we do a quick review, we said that this was our GLUT2 transporter, alright, in our beta cell. So this is our beta cell membrane, and all of this is happening inside our beta cell of our pancreas. Alright, beta cell is one of our islet of Langerhans, if you guys remember. Right, so we said that glucose will come in, right? And another thing is that GLUT2 receptors, or GLUT2 transporters, we should say, are not dependent upon insulin. All right, so it's not dependent upon insulin. So it doesn't need insulin. So our beta cells in our pancreas don't need insulin because it's a GLUT2 receptor. So our beta cells in our pancreas don't need insulin in order for glucose to come inside the cell. So anyway, once glucose, so if we eat, right, we eat a big carbohydrate meal, our blood glucose is high, and then our glucose starts entering our beta cells, right, from our bloodstream. As glucose enters, we said it turns into glucose 6-phosphate, then the glucose 6-phosphate to fructose 6-phosphate, and we said that that whole glycolysis starts to occur, right? And before we get into that, we said that we have our hexokinase enzyme that if we take the muscle cells, for example, and glucokinase in the liver, however, it's the glucokinase, right? I don't know if we said that, but it's actually the glucokinase in the beta cells, right? So I was just giving you the options that we discussed in our glycolysis videos. But in our beta cells, it's the glucokinase enzyme that works during our glycolysis step, all right? So we have our anaerobic respiration going on right now, right? So anaerobic, remember, glycolysis doesn't need oxygen in order for it to occur. So glucose to glucose 6-phosphate, then we said it continues glycolysis, and then it actually makes our pyruvates, right? And then our pyruvates then go to our mitochondria, and then transition phase, we make 2-acetyl-coenzyme A's, which then go to the Krebs cycle, and then we make FADH2 molecules and NADH molecules, which are electron carriers, go to the electron transport chain, we make ATP, right? Now, from here, what happens is that, and before we said on chromosome number 11 especially, right? On chromosome 11, in our nucleus of our beta cell, we said we have genes that get transcribed and translated, right? Transcribed into mRNA, they're translated into proteins. And that proteins, right? So the mRNA is actually translated, right, in our ribosomes into proteins that actually get packaged and reassembled via our Golgi apparatus in our endoplasmic reticulum and end up in vesicles in a hexamer form. So a hexamer meaning one zinc, and on each zinc we have 6 insulin attached, right? So we have 6 insulin molecules attached to zinc, which is called a hexamer, right? Because it's in hexamer form. And for each insulin, for every insulin, we make a C-peptide, and we have some amylin also in our vesicles. But this is pre-stored insulin. We're ready, right? But how do we release insulin? Well, the formation of ATP is really important because if we think about it, if we eat a lot of carbs, right, our blood glucose is high, and if glucose starts entering the beta cells of our pancreas and we start making a lot of ATP because of cellular respiration, that's an indicator, right, that if we're making a lot of ATP, that has to mean that we have a lot of glucose in our blood. If we're making a lot of ATP, that means there's a lot of glucose entering the blood. That means there's a lot of glucose undergoing cellular respiration and a lot of ATP being made. So if it means there's a lot of glucose in the blood, we have to get insulin out. And that's what we're going to look at in this video. All right, so this was the top part, right, of we just zoomed in into the top part of our cell membrane of our beta cell. Now let's zoom in into the sides, all right? So actually any side, doesn't really matter, but just to get the concept down, right, what we can do is that we can draw this side and this side of our cell. Or you know what, let's just draw the whole thing. Okay, so let's say this is one beta cell of our pancreas. We already looked at the GLUT2 transporter here. Okay, we already looked at that GLUT2 transporter. Right now, we're at the stage where we're making a lot of ATP via cellular respiration because there's a lot of glucose. So what happens is that on our cell membrane, of our beta cell, right? So if we drew it right here somewhere, so let's just go and draw it right here. Wait, let me choose a color first, right? Choose orange, I guess. So on our cell membrane right here, we have ATP sensitive potassium channels. All right, so this is let's go and write this down. We have ATP sensitive potassium channels. All right, so ATP sensitive. So remember, this channel will react to the sensitivity of ATP inside the cell. Potassium channel, right? There's many channels of this, but we're just drawing one. So what's going to happen is this. So usually this channel turns out, right? It turns out that usually this channel is open, okay? Usually, because if the channel's open, right, it usually means that there's not much glucose coming in. So if we're in the fasted state, right, so if we haven't eaten anything and we're in the fasted state, we don't want insulin getting secreted, right, or we have a risk for hypoglycemia. Okay, and remember, and we'll see in a bit that insulin is secreted whenever our potassium channel is actually closed, causing a buildup of potassium. But if our potassium channel is open, we don't have a buildup of potassium and we don't secrete much insulin at all. Okay, so here's what's going to happen. We're making a lot of ATP and it's open right now, so we have potassium leaving, right? We have some potassium leaving the cell also. But once there's a lot of ATP will actually go and bind here onto this potassium, ATP sensitive potassium channel, and it'll end up closing the crap out of the potassium channel. All right, so now there won't be potassium leaving. So it's going to erase all of this, right? We'll actually have a huge potassium channel that's actually closed. And how is it closed? Because of the buildup of ATP, ATP will go and bind here. Okay, and once ATP binds, the potassium channel will close. Now, originally, when potassium was trying to go, it can't now. So all this potassium will start bouncing back and start depolarizing this beta cell. Depolarizing meaning that this beta cell is going to start getting even more positively charged, right? Because now potassium is building up inside. Because of high glucose, right? Because of high glucose, we've made a lot of ATP. Now potassium charge is building up because it turns out ATP closes the crap out of this ATP sensitive potassium channel, right? So we have potassium buildup, positive charge buildup inside the beta cell. Now, how does this help release insulin? Well, it turns out that as the potassium charges build up, our total membrane potential inside our beta cell starts to increase, right? We increase in positivity. So then it causes a calcium channel. So we actually have a nearby calcium channel here that's also trying to work, right? So our calcium channel is sensitive to the membrane potential. All right. So this calcium channel is sensitive to the positive charge. All right. So let's go and write this down. So this is our calcium channel here. That's actually sensitive to positive charge inside the beta cell. All right. Now, as positive charge starts to increase, what's going to happen is that you know what, let's go and just make another beta cell here so we have a clear picture, all right? So we can actually relate it during two pictures. So as positive charge builds up via our potassium getting blocked off and can't really leave, we have this calcium channel that opens, all right? So because of the positive charge buildup, our calcium channel opens. Okay, so let's go ahead and show that. So now our calcium channel opens. Now, what does this allow? This allows calcium from the outside, right? Calcium from the outside of the cell to actually enter inside of the cell, and it helps insulin to get out of the cell. All right, so what's going to happen is that calcium will then come inside the cell, and what it's going to do is that you see these preformed vesicles of insulin. It's going to bind to this vesicle, and it's going to transport the crap out of this vesicle outside, because we need insulin in the blood. Okay, so let's say we have the blood right here, right? Our bloodstream running right here. Let's go and draw our bloodstream running right here. What's going to happen is calcium's going to come inside the cell, and we're going to have, let's draw a preformed vesicle here. with our zinc, right? So with our zinc and our insulin, which I'll just show in purple dots, all right? So we have 1, 2, 3, 4, 5, 6, okay? And then we're gonna have some C-peptide for every insulin, but let's just go and write just one C-peptide just to save time, right? But for every insulin, we have a C-peptide released, okay? And also, we're going to have some amylin, okay? So we're going to have some amylin inside our vesicle also. And remember that this is our beta cell, okay? And so what calcium is going to do is going to come here, bind onto here, and it's going to eventually end up exocytosing this vesicle out into the blood, okay? So it's going to come here, it's going to help this vesicle, it's going to bind to this vesicle, and it's going to help this vesicle eventually to exocytose out of the beta cell and enter our blood. So what's going to be in our blood? We're going to have insulin in our blood, right? A good amount of insulin. We're going to have some C-peptide in our blood. So for every insulin, we secrete a C-peptide. And we said that in the previous video, that's C-peptide because you release C-peptide for every insulin. C-peptide is a good way to measure your insulin levels. All right. However, C-peptide has it actually lasts longer inside your blood than insulin does. All right. But anyway, right, and we also have some amylin release. Okay, and some pro-insulin also, but let's just focus on this for now. So you see how this worked, right? So let's go back here. Again, let's just do a quick review. So what happened was we made a lot of, okay, so actually let's start before that even. When you eat food, right, your beta cells have to release insulin. But how does it know that you have high blood glucose? Well, what happens is glucose enters the beta cell through this GLUT2 transporter, undergoes cellular respiration, and starts making a lot of ATP. That's an indicator for the beta cell. It's like, oh crap, there's a lot of glucose because how do we have a lot of ATP, right? So all this ATP will actually start to bind on the potassium channels, the many potassium channels. We only drew one, but there's a lot. It'll bind to the potassium channels, close the crap out of these channels, and this is gonna cause a bunch of positive charge buildup because potassium is positively charged. This positive charge buildup will trigger this calcium channel to open up, okay? And the calcium channels will open up. Calcium will rush in from the outside of the cell to the inside of the cell and will help bind to the vesicle and will help exocytose the vesicle and release the products inside our blood. And now we have insulin in our blood, and insulin can, for example, go to our muscle and fat cells, right, and reduce blood glucose that way by transporting glucose into those cells. All right, and that's how we synthesize and secrete insulin outside of our beta cells. All right, we can even in the future talk about some drugs that act on these channels right here, all right, to either increase the secretion of insulin or to decrease the secretion of insulin. All right, so that's pretty much it. That's all I wanted to get through in this video. I hope this video made sense to you guys. I hope to see you guys in my future videos where we'll talk about more cool topics about biochem, physics, and chem. Don't forget to hit that notification bell, like, and subscribe. See you guys later, and stay safe.